Hello everyone, welcome to our presentations. Today we'll be presenting you two papers from the topic Poetry Generations. So first, let's have a look at the outline of our talk. So I will first give you a brief introductions into poem generations and what the task is about. Secondly, I will be presenting a paper called Automatic Poetry Generations from Prosaic, and later my friend Dan and Ragini will join me and give you a discussions about acrostic poem generations. As we may know, poem writing is an art form, and poem is a kind of literature in which the words are chosen for their sound and the image they suggest, and the words are arranged in a separate line, usually with repeated rhythm, and often the lines rhyme at the end. There has been a lot of work on automatic poem generation, and this is a well-established and challenging task in natural language generations. The challenge here is particularly the syntactics, well-formed, topical coherence that a poetry generation system should be able to deliver. By syntactic well-formedness, we mean that the text generated should be grammatically correct, and by topical coherence, we mean that we should be able to identify and establish links between the word use, the sense, and the paragraph in a poem. Furthermore, we need to incorporate the rhymes constraint and the form constraint into the poem. And last but not least, because poem generating is an artistic field, so our system will need to exhibit a certain amount of literary creativity. There are two main approaches in poem generations. Most of the early system based on rule-based approach, so this system relies on handcraft rules and templates to generate poems. Nowadays, most of research tends to use the statistical approach, which we don't need to mix handcraft rules, and our model should rather learn the statistical features directly from the poetry corpora or the training corpora. So our focused paper today are both using this language model, and a critical point here that they use a neural language model which based on neural network. An automated poem generation system should have the following flow. So first it will receive a seed, and from the seed it will generate the first verse. This first verse will act as an input to generate the second verse, and the system will do this subsequently until it reaches the end of the paragraph token. So in the second part of our presentations, we'll be looking at a paper called Automatic Poem Generation from Prosaic Text. As the title might suggest, the goal of this paper is to generate poems in English and French using a non-poetic training data sets. This is exactly what makes this paper interesting, because up until now, all existing statistical models are trained on or make use of a corpus of poetry by using non-poetic text, which can vary from news on newspaper or Wikipedia article. We can have a much larger training data sets. And the second motivations of the author is to investigate the ability of neural language models in poem generations. So it's interesting if we can adapt this neural language model to generate linguistic and aesthetic aspect of a poem, because in recent years, neural language models have achieved a lot of state-of-the-art in natural language processing, in particular in language generation. So as I mentioned before, the author of this paper want to make use of a neural language model, and here in particular, he adapt the encoder and decoder architecture. This is a very popular architecture in computer visions as well as in natural language processing, and in NLP the famous variant of encoder-decoder is the sequence model, which is largely used in machine translation tasks. We move on to discuss how this encoder-decoder mechanism works. So as an input, we have a list of words or a verse, and the word is represented by tokens embeddings. The encoder will try to construct a context vector from the whole sentence here and pass it to the decoder. The decoder will try to predict the next verb word by word. The other paper had done some of the modifications to the original encoder-decoder architecture to make it a better fit for the task of poem generation. He added some of the additional component here, the attention mechanism, the context vectors, the rhyme prior, and the topic prior. So in the few next slide, we're going to discuss in depth about each of these components in these architectures. So now let's have a look at the first component in our architecture, the encoder. The encoders reads each word of a sentence, and at each time step t, it will compute a hidden state based on the current embeddings, word embeddings, and the previous hidden state. And the result is gonna be the context vectors we've seen previously, and this setting is not very different from the original settings of the encoder-decoder architecture. So now let's have a look at the second component in the architecture, the decoder. It's very interesting because most of the text or poem generating is happening here. So here we see the vanilla decoder with two components, softmax layer and decoder layer, and the decoder that is implemented in this paper. So we can recognize that there is one additional layer which is called the hidden state, attention enhanced version. So the attention mechanisms here is similar to the attention mechanism proposed by Menon, which is very popular. It's intended to alleviate the problem with the original encoder-decoder problems. So I will explain it. Just go back a few slides. So this is the hidden state enhanced with attentions. It's receive the context. It receives the attentions from the decoder. So we can see that it had much more information about the positions of the word here in the encoder part, and basically the attention mechanism tells the decoder which part of the encoder it should pay attention to. So far we have discussed the encoder, the decoder, and the attention mechanism. We are left with the rhyme prior and the topic prior. Before we discuss how the rhyme prior and the topical prior work, we should gain some intuitions about poetic constraint. First, we might ask ourselves, why do we need to add this poetic constraint? Let me remind you that we are going to train our model on a generated text, and it can be a Wikipedia article, for example, and Wikipedia example does not own the poetic character of a poem, such as rhyme. So if we just train our model like that, the output we have will not resemble a poetic verse. And so the author decided to add the two most common constraints of poems is the rhyme constraint and the topical constraint, because rhyme constraint is basically the thing that differentiates poem from other arts of writings. And now we have to take care how can we technically implement this poetic constraint to a neural language model. The author has created a technique that is modified the output probability of the softmax layer with a prior probability distribution to make sure that the words that are suitable have a high probability. So first we'll look at the rhyme constraint. The rhyme constraint is applied on the last word of a verse to make sure that it has the same rhyme as the last word of the previous verse. Because we're regenerating the verse in reverse, that's why we're applying it on the first word here. And this is implemented by using a phonetic representation of word, which it creates from Ragini. From these representations, the author create a probability distribution for a targeted rhyme sound and then use it as a prior distribution to reweight the neural network standard output. In order to make words in a poem coherent to a certain topics, the author of the paper apply a method called based on Latin semantics model based on non-negative matrix factorizations. It makes intimidating. However, in essence, this method trying to create a probability matrix between a word and a certain topics, and he will apply the probability of a word on certain topics into the last layer of the decoder. At the first attempt, this direct approach has corrupted the syntactic fluency of the sentence. In another word, it's create grammatical incorrectness in the output sense. So the author came up with some remedies in which he only add the topical constraint when the entropy of the last layer here is very high, which indicates that the model is quite uncertain about the word use. And when the entropy is low, we shouldn't add any additional topical constraint because the model is sure about its word choice. So the author claimed that by this method, he is able to create a syntactically well-formed sentence. In order to train the model, we just discussed about the author used the common corpus, which is a generic web text, and from this corpus he only keeps sentences that have up to maximum of 20 words, and keeps the sentence that contain list of the function word from a predefined list. By this, I guess the author means that he will only keep sentences that belongs to certain topics. And there is some statistic on how big is our training data. It has 500 million words, and it has a vocabulary of 15k word with high frequency. The word with the low frequency will be replaced with the unknown tokens and a frequency of 0. Quantitative evaluations of poems created by machine is a very complex task due to the nature of poems. So in this paper, the author asked 22 annotators evaluated 40 poems based on 4 criteria: fluency, coherence, meaningfulness, poeticness, and give the score for each of the points from a scala from 1, the lowest score, to 5, the highest score. So before I show you the final result of the evaluations, let's have a look at the sample poems that generated by the models here. So we have 4 verses of poems, and we can see that the poetic constraint definitely work here, because the end of each line, the word at the end of each line definitely rhymes together. Impossible, immortal, evil, ill, and at the first look, this poem does really resemble poem that's written by human.
Hello everyone, I'm Huang. Now I will introduce the content of Acrostic poem generation. The first part is background and motivation. The second part is data preprocessing. The third part is the first model, neural poem language model. And the rest of the content will be introduced by my teammate. So first, what is a Acrostic poem? It's a special type of poem. It has common features like formal feature, content feature. Formal feature means the first letter of each line should form a complete word. For example, here, The first letter of each line can spell out the word ending. So ending is the acrostic word. It's also the topic word. And the content feature means the content of the poem should relate to the acrostic word. As we can see, there are some words like done, and in the end of the last, it can show that the content of the poem is related to the topic ending. And in the model of acrostic poem generation, it has some additional features, like the end words should follow a rhyme scheme, and the length of the poem should only be 4 to 8 lines. So why do the author want to do the research about acrostic poem? Because it's a new task in the area of computational creativity. We all know the creation of acrostic poem is full of creativity. It's hard for human beings to write acrostic poem, so it's even harder for a machine to generate it. The development of creative machines is a very important step. So automatic poem generation plays an important role at the intersection of computational creativity and natural language generation. There are two main challenges in this topic. One is semantics, the other is structure. So semantically, the poem should follow a given topic and the content should also be coherent. And structurally, the poem should rhyme and contain a acrostic word. So let me introduce the baseline model. It's also called Nguyen point. It's a generated model. And it consists of two components. The first one is here. It's the conditional neural language model. It will produce an acrostic poem according to a given word. And the other component is rhyming model. It will produce the last word of every line to follow a rhyme scheme. And there is a topic prediction model. Actually, this model is not directly related to the process of generating a poem. It's just to increase the data set. And now let's see how this three model connects to each other and their data sets. There are 4 data sets in total: known topic poems, unknown topic poems, Wikipedia, and sonnets. So the first model is topic prediction model. It will be trained on known topic poems in order to learn how to predict the proper topic for a poem. After that, unknown topic poems will be fitted into the model. Then it will translate, and then it will transform into known topic poems. So this will create more sufficient data for the next model. And these two parts of the data set here will be preprocessed. It means the poems will be split into lengths of 4 to 8 lines. And the second model is neural language model. It will be first pre-trained on Wikipedia in order to improve the coherence of the generated output. Then it will train on all known topic poems in order to create acrostic poems. And the last one is rhyming model. It will be trained on sonnets in order to create rhyme scheme. So now I will talk about the neural poem language model in details. It models the probability of a poem X as the formula here. And X0 is the start word of a sentence. U is a given topic. V is the acrostic word. W is the length of the poem. This model is a 3-layer unidirectional, long short-term memory. LSTM language model. As we can see in the picture here, the start word, topic word, acrostic word, and the lamps will be fitted as input to the model. It goes through LSTM linear layer, then it generates the first word. The new generated word and topic word, acrostic word, and lamps will be fitted into the model again and again. So let me take a more specific example here. Suppose that the machine wants to produce an acrostic poem in the topic of ending. And the first sentence, the first word is everything. So now the everything, ending, and the length of the poem is 6. These 4 parameters will be fitted into the model. Then the model generates the first word, that is. Then is ending 6 will be as input fitted into the model again. Then it generates the second word, is done. The third word is at. Then the random quality. And all word level inputs will be represented in global embeddings. And the length will be set to a single-digit tensor. So as we know, the first word of each line should start with the indicated letter, and it should also guide the poem's content. The content should relate it to the topic word. It's not just random words. So how to choose the first word? The model here used the Kann technique, that is the K nearest neighbors. It's a supervised machine learning algorithm. It assumes that similar themes exist in close proximity. For example, here, the word man, sir, and king, they share some similar meaning, so they are relatively close to each other. And how to measure the distance of 2 words? This model uses cosine similarity to measure that. For example, if we want to calculate the distance of the word man and sir, it will be calculated as the embedding of man times the embedding of sir divided by the norm of the embedding of man times the norm of the embedding of sir. So in details, the model will take 5 nearest neighbors to the topic word from all the words in the vocabulary that start with a specific letter. And then you should choose one from these 5. And with probability of 0.7, it will choose the one with maximum conditional probability given previous words. If just doing so, the output will become frequently incoherent. So in order to achieve coherence, with the probability of 0.3, the model will sample all the first words from the language model and masking out all words that start with the wrong letter. So let's talk about the last punctuation of each line. So as I mentioned before, the poem should only in the length of 4 to 8 lines. But how to make sure that happens? So the model will be fitted an embedding that represents the lengths. And if the poem is too short, the model will substitute each end of sentence symbol by end of line. If the poem is too long, whenever If the poem is too long, the model can do the same the other way around. Whenever this will lead to the last symbol of a poem is comma or semicolon, it will be replaced by a period. And now the rest of the content will be represented by my teammate.
Okay, hello everyone. I'm Ragini and I'm part of the Poetry Generation group, and I'm going to continue speaking on acrostic poem generation. So the second model in the baseline model is the rhyming model, and this is used to generate the rhyming word for the last position in each line. And this is trained on sonnet data. Because sonnets have certain rhyming schemes, and this makes it easier to train the neural model accordingly. So the rhyming model generates poems with certain rhyme schemes depending on the length of the generated poem. So a 4-line poem would have an ABAB rhyme scheme. A 5-line poem would have an ABABC rhyme scheme. A 6-line poem would have an ABABCC rhyme scheme, and so on. Now, the probability of the output word C, which is the rhyming word, is modeled as given in the equation. And this takes into consideration certain parameters, such as the first word of the rhyme pair, which is denoted as A, and the poem generated up to the output word, which is denoted as B. Now, the rhyming model is a 4-layer unidirectional LSTM language model with hidden layers, and the rhyme encoding LSTM and the poem encoding LSTMs have one hidden layer, but the rhyme encoding LSTM has 256 dimensional hidden states, and the poem encoding LSTM has 512 dimensional hidden states. Now, if we look at the image here on the right, we can see that the topic, the acrostic letters, and the number of lines are fed into the LSTM. And through a linear layer, they generate a certain word, and the process is repeated again for the next word until the end of the line, when the rhyming model is used to generate an output word, and then this again goes back to the initial generation in the next line for the first word. So how exactly is the poem generated? Well, words generated by the rhyming model substitute the last word in lines which are second in a rhyming pair. So in a 4-line poem with an ABAB rhyme scheme, the last word of the first line serves as an input to produce the last word of the third line. And similarly, the last word of the second line is again used as the input to produce the last word of the fourth line. So if you look at the poem on the right, you can see that the last word of the first line, child, is used as an input to produce the last word of the third line, wild. And similarly, the last word of the second line, you, is used to produce the last word of the fourth line, view. So these are rhyming words: child, wild, you, view. So when the rhyming model takes into consideration the output word, it generates 5 candidates, and the final word that's used is the candidate word with the highest language model probability. Now, the third model in the baseline model is the topic prediction model, and this is required to make sure that the poem is related to the chosen acrostic. And it's used to create topic annotations, since the poem generator requires a topic for each poem. The probability of this poem is depicted as below, and it belongs to a certain topic Y. And it takes into certain parameters, such as the start of the sequence token, the end of sequence token, and bidirectional word level LSTM. Now, the topic prediction model is essentially used to create silver standard topic annotations, that is, automatic annotations. And it is trained on the known topic poems data set, which consists of 144 topics and a total of 32,786 poems. And the topic prediction LSTM has one hidden layer and a hidden size of 1024. So the authors of the paper decided to, sort of conduct certain experiments. And in order to conduct these experiments, they had to select a model as the basis for the neural poet. So they trained certain, they trained multiple language models, which were essentially trained on certain data sets. And, their perplexity scores, that is the measurement of how well these models predict certain samples, were considered, when selecting a base for the neural poet. So these models are the goal model, the pred goal model, and the wiki models. And the goal model essentially refers to a language model trained on goal poems, that is the known topic poems data set. The pred goal model was also again further trained on known topics and unknown topic poems data sets. And the wiki model was pre-trained on Wikipedia and fine-tuned on a combination of known topic poems and unknown topic poems. And it was found that the Wikipedia models obtained the lowest perplexity scores. This is because pre-training on Wikipedia results in a certain coherence in the generated poem, because articles on Wikipedia are written in complete sentences and have a certain readability to them. So the authors also decided to have human evaluations of the generated poems to assess the quality, of these poems as well. So, the human evaluators basically considered 40 poems generated using certain words in this table on a scale from 1 to 5, with 1 being the worst and 5 being the best. And they evaluated these poems on the basis of readability, that is the lexical and syntactic coherence, meaningfulness, that is if the poem can be interpreted as conveying a message to the reader, or if they could be close read or something, and poeticness, that is if the poem essentially reads like one, so if it rhymes and it looks like a poem. And the authors basically considered certain models of the neural poet, which is the baseline model, and each model had a certain feature turned off or a certain feature not considered. So the neural poet model served as the baseline model, and this performed well in most of the evaluations. It was, again, as mentioned before, it was pre-trained on Wikipedia and fine-tuned on known topic poems and unknown topic poems. The neural poet ST is the same as the baseline model, but it doesn't choose the first word of each line from the nearest neighbors of the topic. The third model, that is the neural poet STAC, has switched off acrostic forcing. So, they don't enforce the first letters to spell out the acrostic word. But because the language model receives embeddings of certain characters as the input, the neural poet STAC, largely tends to produce the acrostic word. But the language model, has more freedom to generate coherent and fluent text. The neural model STRH is the neural poet, but without the rhyming model. So the last words are generated directly from the language model, and the final model is the neural poet STTP, which doesn't receive any topic as input. So it was found, so human annotators evaluated generated poems and gave certain feedback. So it was found that Neural Poet, which is the baseline model, performed well in most of the evaluations. And Neural Poet ST had only certain small differences in scores, for the poems generated, but as well. And the Neural Poet STAC found that the poems generated, resulted in poems that are generated, resulted in poems that are more fluent than most of the other models. And differences to the Neural Poet are quite small, which means that, despite, despite enforcing acrostics, not much quality is lost. The version of the Neural Poet which doesn't have the rhyming model actually receives the lowest scores. It seems that human annotators tend to value rhyming in poetry, so this sort of emphasizes the importance of the rhyming model in the Neural Poet. And finally, in the model which doesn't take topics into consideration, doesn't receive a topic as an input, actually obtained the highest, closest to highest scores for most of the individual evaluations. And it was found that these generated poems are more fluent and coherent than the others, but they don't relate to any specific topic, which results in a small drop in quality for poeticness. And this is why the Neural Poet, that is the baseline model, is generally considered to be the best of all the models that are run. So looking at the scores given by the human annotators, as mentioned, the Neural Poet has the highest performance for fluency and for poeticness, for known words, and also the best poeticness score for all. In the Neural Poet ST, that is the model without the first word related closely to the neighbors of the topic, the differences in poeticness are quite large. As we can see here, for all it is, the poeticness was ranked as 3.25, but for known words it was ranked as 3.31, and unknown words it was ranked as 3.20. So there's quite a big difference, especially with known and unknown words. The Neural Poet STAC, that is the model without acrostic forcing, resulted in highest fluency scores for all and unknown, as well as the highest meaningful scores for known and the second highest meaningfulness scores for all. And as you can see, the Neural Poet STRH, that is the model without the rhyming model, actually resulted in scores in the lower half for all the individual evaluations. And the Neural Poet STTP, which is the model without the topic input, resulted in highest or close to highest scores for most individual evaluations. So topicality was also another aspect that was evaluated, and this was used to check if the poem's content relates to the input word. So acrostics were generated during these evaluations, and 40 poems were created using these acrostics, using two models. The first one being the final neural model, the baseline model, which is the Neural Poet, and the Neural Poet with the topic input being 0. So it was found that the poems generated by the Neural Poet tend to be closely related to the topic for more than 50% of the total number of poems generated. But in about 15 cases, the two annotators disagreed. In 4 cases, it was found that the poems generated by the neural poet STTP, that is the model which does not know about the topic, was found to be more similar to the neural poet. And 12 poems out of 20 were recognized for the known words, and 9 out of 20 were recognized for unknown words. So what are some of the observations that the authors found made while conducting these experiments? Well, one thing that they found was that the poems generated tend to confirm with the topic given by the acrostic word, and the model actually worked well even for topics not seen during training. Actually, the model worked well, as we saw in the previous slides. The model worked well for a 0 topic input as well. And the usage of explicit representations of topics resulted in the poems being more coherent. This was something that certain previous studies didn't really take into consideration, and their results tend to be quite different. And it was also found, especially in preliminary experiments, that character level models learn easily to generate acrostics by themselves, but they don't follow the topic as coherently as word level models. And one of the major observations was that, the certain constraints that were imposed only decreased the fluency and meaningfulness slightly, but actually increase the poeticness of the generated poems, which shows that the acrostic poem generator generated poems of certain value, and provided poems which were readable and were quite quite closely connected to that of what a human poet might write. So what can we conclude from this paper? Well, for one thing, the acrostic poem generator tends to produce poems that are readable and poetic, as evidenced by the evaluations by the human annotators. But there are some improvements that can be made, for instance, incorporating other poetic devices such as metaphors and symbolism. And it would be good to be flexible with the rhyming model, as the acrostic model tends to hard-code the rhyme, and the prosaic model only rhymes on the last word of a verse. So it would be interesting to see a rhyming model which mixes things up and produces poems that are more close to that written by a human. So that concludes our presentation, and we hope you enjoyed it, and we look forward to hearing your questions during the live session. Thank you.